record on this computer. I also want to say that my office hours now are going to be via Zoom because nobody came, or essentially nobody came when I sat in the courtyard of Pais. Also, it's getting cold. And so what I'm going to do is I'm going to hold office hours from 3 to 5 on Mondays and via Zoom. I'm not going to record these sessions. I'm just going to have them be just live sessions. And what I'll do is I'll be sitting here at my desk in my home office, and I'll turn on Zoom. I'll send you all a Zoom link, although you already have had that Zoom link 20 times already. Anyway, I'll send you a Zoom link, and if you have a question, just fire up Zoom on your PC and turn on audio and speak up and ask your question. And I'll do my best to answer the question. I'd prefer it if you wouldn't ask me to do homework problems for you, but on the other hand, I suppose it would be legitimate to ask for hints or for an explanation of what is meant by a particular homework problem. So let me now do some examples and talk about what I had intended to talk about, as examples today. And so let's see where it was that I was going to start today. Right, all right, it's a little bit farther on. Getting warm. All right, I think this was basically where I intended to start. Let me make this bigger. And let's see, where is it that I think. Right, what I was going to do was to say something about these self-adjoint systems as an example. Oh, first, I also want to go through the WKB in a clearer fashion. So let me maybe start with that. I did go through this yesterday, but I think it'd be wise to do it again because it occurs in quantum mechanics, and it's quite a general way of solving approximately a second order ordinary differential equation. And this is a homogeneous ordinary differential equation. There's a zero here. Everything has y or y prime or y double prime. And what Jeffrey suggested was you set y equal to e to the z, and that allows you to easily form what the first and second derivatives are. You pop them into this equation, and you then have z double prime plus z prime squared plus pz prime plus q equal to 0 after you factored out an e to the z. And but now this is a nonlinear equation, and nonlinear equations are very hard to solve, but what Jeffrey's noticed was that you can actually solve this thing if you drop the second derivative initially. And so you just solve for the lowest order solution, z0, as z, keeping just these three terms. So z0 prime squared plus p z0 prime plus q equals 0. And we know what p and q are. You're given those. And so what we then do is solve the quadratic equation, and we find z1. And once we have, I'm sorry, we solve this quadratic equation for z0 prime. Then we differentiate z0 prime to get an approximation for z double prime, and then we substitute that approximation for z double prime into this expression where we've already solved for z1 prime. And at this point, then, we've got another quadratic equation for, here we had a quadratic equation for z0 prime. Now we have a quadratic equation for z1 prime in terms of z0 double prime, which we solved with a previous approximation. So then we solve for z1 prime, and then we integrate it. And of course, z1 prime just means our best guess as to what z prime should be. And if we integrate z prime, we get z, and y was e to the z of x, and so that's our solution. And so in particular, if we apply this technique to the time-independent Schrodinger equation, which is this, and what I've done in the last, well, I see I haven't, well, I guess I have done it. Well, now I'm not certain that I got all the minus signs. What I did was I got rid of the extraneous minus signs. And so this thing is actually then, if we let psi equal to e to the w, psi prime is this, psi double prime is that. So the left-hand side then is w prime, w double prime, good God, plus w prime squared times e to the w. That's the left-hand side. And now I see there's a minus sign that I didn't get rid of. What I did was I got rid of most of the minus signs. And so here I'll be fixing that. And let me also fix it here in, let's see, we want to go back. Let me go here. All right, so this is our equation, and now again in this thing we're going to initially drop the w double prime, and so we just have the w0 prime is equal to the square root of this right-hand side, and we're going to then set w0 double prime, of course, is the derivative of that, and that is just this expression here. And so then when we substitute into this equation, what we have is that w1 prime is the square root of this minus w double prime, and w double prime then is w0 double prime, and so that's this thing, and we then get our approximation w1 prime then is this big square root. And now if we expand the square root, we get basically just we get an extra factor of a half because it's a square root, and so we get basically minus v prime over this, and of course we have to factor out this term, and anyway, so that's what we get. And all right, I see I've done something dumb here by repeating. This is the same as that. So obviously I was not thinking carefully here. That's the trouble with a mouse. You mouse something in, you LaTeX it, looks beautiful, and so you think it's right. But what I actually had was an intermediate step here, and then that is equal to that. And so the intermediate step dropped out, and I'm not going to try to put it in. Let me get the chat thing going. So type on the chat if you want me to cough up the intermediate term here. It's something I can do if you want me to. Anyway, once we have W1 prime, we put it in the exponent and integrate. And then you see this thing is actually the derivative of the logarithm of V minus E. I think that's the term that's what I meant to have there. Yeah, that's right. So maybe I should fix this on the fly now that I mention it. In fact, it's conceivable that I fixed it correctly in this version. No, that's wrong also. Okay, so this thing here is actually so it's minus, and let me get rid of that. So it's minus log of, and I should put a backslash here, log of V minus E prime. So the log of V minus E prime is 1 over V minus E times V prime, but there's a 1/4. There's a 1/4 there, and so this, and 1/4 the log is V minus E to the power 1/4. So I'm going to stick that in, namely 1/4, like that. All right, let's see if this shows up correctly then. Right, it's the derivative of log of V minus E to the 1/4. And what I guess we need here is it's log, whoops. So it's the derivative of the log of V minus E to the power 1/4. Anyway, once we integrate that, we get the either V minus E or E minus V to the 1/4 apart from an overall factor of I. And then we have to integrate this thing, which is either I or minus sign of this square root. If E is greater than V, you get an I because you started out with V minus E. So if E is greater than V, you get an I. If V is greater than E, then you get a minus sign. And that's where the damping occurs. And it was a similar thing that was done here. Okay, now well, I don't know if that is okay, but let me say we were talking about self-adjoined systems, and one example for that is the second order differential equation minus u double prime is lambda u. So this is a simple example of this of a system of self-adjoined system, differential system. So this is a formally self-adjoint differential operator because, you know, how could it not be? We're thinking of an interval a to b, a and b finite. The differential equation is LU, which is minus u double prime equals lambda u. The function p is 1. We're going to choose the interval from minus pi to pi just to make things simple. D then is the set of all functions u that are twice differentiable and satisfy the Dirichlet boundary conditions. U of minus pi equals 0 equals u of pi. Then we get this then is a self-adjoint differential system. The domain includes linear combinations of sine nx, because sine pi vanishes, sine n pi vanishes, and sine minus n pi vanishes. If we impose Neumann boundary conditions, then the domain D is a linear combinations of cosine nx. And in some cases, some differential systems, of course, are self-adjoint but singular, because the function p vanishes at one or both and the endpoints, or because the interval is infinite, like 0 to infinity or minus infinity to plus infinity. And in these singular self-adjoint systems, if they are self-adjoint, then the boundary term vanishes and D is D star. And this is typically the situation in quantum mechanics, that we have self-adjoint differential systems. One example of a singular system is Legendre's system, and in particular, that's where L is minus d by dx, 1 minus x squared d by dx. The differential equation is LU is L plus 1u. And the interval is minus 1 to 1. P is the coefficient here. It's 1 minus x squared. So it vanishes at both endpoints. And by the way, the reason why you want P to be non-zero is because when you try to minimize the energy of the system, which is to say, how shall I say, can I find it here? Let's see if I can find, no, it's not visible there. So let's go back here. It's further on. Oh God. Well, anyway, the point is that when you apply the principle of least action, or you apply the Lagrange multiplier technique, as we did, I think, yesterday, you need to have the condition. You have something like. So let me just insert it as a. You have something like an integral of, in this case, it's u double, you have something like u prime squared plus maybe pu dx, and you want, or pu squared dx, and you want to be able to conclude from that something like, you'll have u prime variation of u prime plus p u variation of u, and so that is minus u double prime variation of u plus pu variation of u, and you want to be able to say that therefore minus u double prime plus pu is equal to 0. That's the differential equation. And or if you put in the Lagrange multiplier, then what you'd have that would be that this would be lambda u, say, and we'll get to that. I'll get to that in a moment. We did it last time though, and in order to get there, you see, you have to be able to say that this coefficient, that this p is non-zero. Otherwise, you can't conclude that u double prime plus pu equals lambda u. In other words, this pu, if p were 0, you wouldn't get any information about u. Well, anyway, I guess that's not terribly clear, and in fact, now that I think about it, it's not so clear in my mind either. So let's just say that that's one of the requirements, that p is positive, or non-zero at least. And but on the other hand, it is 0 at the endpoints. But on the other hand, the boundary terms, which are proportional to the Wronskian of u and v, that does vanish at the endpoints because it involves p. It's linear in p, and so p vanishes there. So it's okay. And the domain D is a set of all functions that are twice differentiable on the interval -1 to 1. The Hermit system is another formally self-adjoint. Well, this is the Hermit differential operator. It's formally self-adjoint. The differential equation is minus u double prime plus x squared u is an eigenvalue times u on the interval. P of x is 1, q of x is x squared. But now it's singular because the interval is infinite. It goes from minus infinity to plus infinity. And so the domain D consists of functions that are twice differentiable and go to 0 suitably fast, so that the boundary terms, well, the boundary terms vanish because u and v vanish as you go to plus or minus infinity. And so that's another example. We saw last time that you could make operators self-adjoint. And we saw that one nice property of self-adjoint operators is that when you use Wronski's method to find a second solution, the Wronskian is particularly simple for a self-adjoint operator. And in fact, the Wronskian for a self-adjoint operator is just 1 over p, apart from a constant. And so the trick for finding the second solution is very simple. It's the first solution times this integral 1 over p times the square of the first solution. And so, for example, Legendre's differential equation, which is formally self-adjoint and is part of a singular self-adjoint system. An obvious solution for L equals 0 is P0, which is equal to 1. So the left-hand side is 0, the right-hand side is 0 because L is 0. And since P is 1 minus x squared, the formula for the Wronskian is P0 of x times 1 over P0 of x times P of x prime. P of x prime is 1 minus x prime squared, but P is just 1. And so we have to integrate this. And the integral of 1 minus x prime squared is just this log of this ratio. And now we see that this is a solution that's singular at both ends of the interval. And so it doesn't satisfy Dirichlet or Neumann boundary conditions. So that's why when we work with Legendre's differential equation, we focus on the solutions that are polynomials, and they're called the Legendre polynomials, and they're the first 20 or so are graphed on the cover of the book. So last time I showed you how to make first order self-adjoint differential operators, and we went through that, and then we find that the momentum and the angular momentum and the momentum in a magnetic field, these are all self-adjoint first order differential operators. This is the thing that I was talking about a moment ago when I said you want to have P non-zero, so that when you do the well, when you do this, basically you say you use Lagrange multiplier technique to minimize the energy subject to this normalization condition. So then you have a functional, it's a function of lambda and a functional of u, and you then minimize this. And because P, you want P to be non-zero in order for this term here to make sense. If P were identically zero, you'd wind up with something inconsistent, because it would tell you that you get an equation here that would just be that Q would have to be lambda rho identically. So that's sort of a silly special case. So let's, actually, remember back when we were just a moment ago talking about the simplest self-adjoint second order system was minus u double prime equals lambda u. Well, that's effectively the same thing as an infinite square well potential. And then the conditions here are that the wave function should vanish at A and B, and the other ones also vanish at A and B, and something like that. And the solutions are actually over here. They're sine of n pi x minus a over b minus a, and normalization factor. The lambdas, which are the energies, are 1 over 2m times n pi h bar squared over b minus a squared. And so these are the energy levels in an infinite square well potential. The particle is confined in here because the potential here is infinite. So if you applied WKB over here, what you'd have is you'd have e to the minus. So over here, what you'd have is e to the minus an integral of square root of v minus e dx prime up to x. I'm leaving out factors. But since v is infinite, this thing is identically zero for outside, for x not in AB, or not in the open interval AB. So if this were a finite square well, then the wave function wouldn't have to go to zero. It would instead go to some finite value, and then it would trail off exponentially and die off exponentially. But here, because v is infinite, it dies off completely instantly. Another example, which is one we were just talking about, was the harmonic oscillator. And I think maybe I'll say a few words again about the harmonic oscillator. It's really the archetypical system of physics, especially bosonic, at least bosonic physics. What you have is you have this differential equation, and it's a singular self-adjoined system. It's just the Hermit system, actually, and because it's d by dx squared and then x squared. And you can factor this left-hand side, which is really useful. You write it as h bar omega times, and then what's left is an x minus something times d by dx times x plus something times d by dx, and then this plus a half. And the ground state then is given by x h bar over m omega d by dx on the ground state wave function is zero. So that's just this thing right here. That differential equation then has a simple solution. It's a Gaussian centered at zero. And let me get, gosh, I wanted to just move this out of the way, but I guess I don't know how to do that. So it's just this Gaussian, and the reason it's easily soluble is that we factored this thing. You see, a second order differential equation is kind of hard, but first order equation, you have a recipe for solving that. We went through that a couple of periods ago, and you can solve any first order ordinary differential equation, and at least linear. I think, yeah, we were talking linear. Anyway, the solution is that, and the higher order states are just given by acting on the ground state wave function, which is this, by powers of this. And the way we think about this is we say A, the annihilation operator or the lowering operator, is this factor times x plus IP over m omega. Well, p of course is h bar over I, so this is this h bar over m omega term, and this one here is minus h bar over m omega. And then if you take the commutator of these two things, and of course use the fact that the commutator of q with p is equal to I h bar, or equivalently, the commutator here of x with p is I h bar. Then you see that the commutator of a with a dagger is 1. And the nth excited state is 1 over n factorial, a dagger to the nth times acting on the ground state. So that's how we think of it. And this carries over into quantum electrodynamics or quantum optics. You have an annihilation operator and a creation operator for every mode of the electromagnetic field. So in particular for every photon momentum, and then for each polarization. And so you can imagine it's positively polarized, or right-hand polarized, or left-hand polarized, according to whether the spin is parallel or anti-parallel to the momentum. And you then have a harmonic oscillator for each mode. And so the actual Hilbert space of states is just absolutely gigantic. It's infinite dimensional for every mode, and there are infinitely many modes. So this is something that is kind of scary. And the reason Glauber won a Nobel Prize is that he showed how you could understand quantum electrodynamics in a way that that fitted very well with atomic physics and with classical electrodynamics. And one of the things that he used was coherent states, which are eigenstates of the annihilation operator. So A on Z is equal to Z, where Z is just a complex number. Whoops, sorry. Z is just X plus IY. Arbitrary X, arbitrary Y. So let me see. Let me do a little bit of this perhaps, but I don't understand. I'm moving my hand on this, but it's not moving. You remember the Frobenius method. The idea was you had a differential equation of this form. This is our standard differential equation. And what Frobenius said was, well, multiply that by x squared, because when you differentiate y twice, your powers of x go down by 2, and consider this equation: x squared y double prime plus xp y prime plus q. Here, xp of x is x squared capital P, and q is x squared. In other words, you multiply this equation by x squared, and so q is x squared big Q. Xp is x squared big P. And so then you say that y is x raised to the power r, sum n equals 0 to infinity. And the idea here is you choose r so that the lowest order term, A0, is not 0. And so y is then this, y prime is that, y double prime is this, just ordinary calculus. And then you have that this differential equation then takes this form. Differentiating twice, you get n plus r. Here, let me pull this down a bit. You get n plus r times, well, there it is, n plus r minus 1, an x to the n plus r, because you multiply by x squared. P of x sum n plus r an x to the n plus r, q of x an x to the n plus r, and so forth. And then you solve for r, because r is, you look for the lowest power of x, and that's for n equals 0. And then you set the coefficient of the term with n equals 0 here to 0. And that is, since n is 0, it's r minus 1 plus p of 0 times r plus q of 0 times a of 0 x to the r. And the coefficient of x to the r has to be 0. So this is 0. This is the indicial equation. It's a quadratic equation for r. And these are the solutions. And remember that Fuchs said you're always safe with the bigger root. And that's the bigger root. And I'm going to leave that at that point. I'm going to stop this particular thing at this point. Switch now to something else, namely I'm going to try to do some more examples here. And in particular, let's look at, I think, number 20, because Right, because 14 through 19 is the homework assignment. It's not the next homework assignment, but it's the one after that. So I don't want to start doing the homework problems. Let's suppose we just do this. Let's look at Legendre's equation, and we want to show that the points x equal to plus or minus 1 and infinity are regular singular points of the equation. Well, we know they're singular points because, well, x equal to infinity is always a singular point, or is always a, well, I forget whether it's actually in general called singular, but we have it. Yeah, I think it is always singular. Anyway, that's a question of definition. So maybe I should try to get us to what the definition was. So let me go back to I guess it's Fuchs's theorem. Or was it before that? I'm trying to find out where we talked about singular points, and now I can't. Ah, there it is. It's before that. Yeah, I should have called this singular points because that's all that is about, isn't it? It's just singular points. So let's see. No, we just call it the point at infinity. So we don't say we don't call it a singular point. But so let me come over here and let me get, oh, Jesus. Hold on. I am getting confused. I've got so damn many. Right. All right. Well, let's just stay with what's here. So this is the solution here. And we want to show that these are regular singular points of the equation. And so the second derivative of y is just by the Legendre's equation. It's 2x over 1 minus x squared y prime minus LL plus 1 over that. And that's the same thing as, and we can write that as minus big P y prime minus big Q y. So this obviously diverges when x is equal to plus or minus 1. So these are singular points. But on the other hand, they're not bad singular points, because if you multiply by x minus 1, you see x minus 1 times p, we get something where the x minus 1 terms cancel. We just get 1. And if we go to the other limit, x going to minus 1, we have x plus 1 times p, and the x plus 1's cancel, and we get 1. And if we now look at q, well, what's q? It's this thing. We multiply q by x minus 1 squared, we get something that exactly cancels. And setting x equal to 1, we just get 0. And here, setting x equal to minus 1, we also get 0. So these are all finite. So x equal to plus or minus 1 are regular singular points of Legendre's equation. Point at infinity, on the other hand, we the recipe or the definition is sort of elaborate, and I basically skipped it in class. What you do is you set z equal to 1 over x, and then you compute these limits. Limit as z goes to 0, which is the same thing as x going to plus or minus infinity. 2z minus p of 1 over z divided by z squared. And if you work that out, it's then this, which then is 2 over z plus this, and as z goes to 0, this actually all cancels, although it's not. All right, let's see. As you see, as z goes to 0, this term is just 1. This term becomes minus 1, so this is 2 over z minus 2 over z, and that's 0. Over here, you take q of 1 over z divided by z to the 4th, and you get this expression. And now, because we've got an extra factor of z squared, we actually get something that's infinite, 2 over z squared times minus 1, essentially. And as z goes to 0, this goes to infinity. So the point of infinity is singular. On the other hand, what you do to see whether it's regularly singular or essentially singular is you do these two things with z instead of z squared, and with z squared instead of z to the 4th, and then, well, there's no problem here, you get 0 again. But and then over here, what you get is you have z squared, and you can then rewrite this in this form, and this just becomes minus 2LL plus 1. So this is finite, and so the point in infinity is what's said to be a regular singular point. I think maybe I'm not going to do this now because it's just a little too elaborate. Just so many indices and indexes, you change indexes, and so it's all sort of complicated. I don't see anything in the chat. So we want to derive the recursion relation for r equals 1, but the question was, what was 7.39? So let me see if I can describe that. Well, this is Legendre's equation, so we want to derive the recursion relation for r equal to 1. And so if we set r equal to 1, what we have then is over here, we have basically this equation with r equal to 1, and then p and q are the p's and q's of Legendre's equation. And it turns out we then get this expression here. And then we look for the coefficient of x to the n plus 1. That gives us this, which we can rewrite as that. If we want that to be 0, we get this recursion relation. So that was a little brief, but I don't know. I hope maybe like this. So it's in the video. If you pause the video, you can see that. We've got 2 minutes. Maybe we can look at another one. Example, this again is Legendre's equation. Show that the solutions with the roots are the same. So remember that Fuchs in his theorem said if the solutions of the indicial equation differ by an integer, then the bigger solution gives you the bigger value of bigger solution of the indicial equation gives you a solution to the differential equation, whereas the smaller one may not give you a linearly independent solution. It may or may not. And so if we look at the recursion relation, in fact, this is the recursion relation, but now we go, oh wait, where's r? What did I say? Oh, I said r equal to 1. So what we have to do is we have to go through this, but we set r equal to 0. And the recursion relation for r equal to 0 then looks like this. And Well, we then find that in fact it's the same solution. I'm sorry, I didn't quite let me change the C to the X to a C. Well, we're basically out of time. The hydrogen atom, of course, is another example that's really, really very important. Well, all right, the class is over, so I'm going to stop now. I'm going to stop sharing. That's my son calling, and